This video accompanies the organizer concerning calculating enthalpy with bond energy. So this is the one theoretical way that you are going to learn this year to calculate the delta H for chemical reactions theoretically. So calorimetry lets you calculate it experimentally. You measure temp changes as a reaction occurs and so forth. But this is how we can compare that number to what the answer should be. So this is the way you're going to calculate the theoretical delta H's for chemical reactions. So there's a lot of writing already on your organizer. One of the big things to keep in mind is that this is all about chemical reactions. So whereas heating and cooling curves took a look at how IMFAs change and so forth, this examines the intramolecular bonds breaking, so the covalent bonds that are involved when a reaction takes place. And so we're looking at, once again, potential energy. So we're looking at a delta H. So we just want to define bond energy for you since we're using bond energy calculations. Bond energy is defined as the amount of energy required to break a bond and therefore separate two atoms. Units of bond energy are typically kilojoules per mole, and it changes depending upon what the atoms are. So you actually have an appendix with bond energies. It is, I believe, Appendix 6, although I could be wrong because it seems like things have changed a little bit, but it's this one. So you've got a huge list of bond energies. Yours may look a little bit different than this one. This is an older version. Yours may be grouped a little bit differently, but notice that the units for bond energies are kilojoules per mole. You've got all these different, notice that we're focused mostly on the nonmetals because those are the things that form covalent bonds. Ionic substances with ionic bonds are where the metals come in, so you don't really see metals here. So bond energies is really about the covalent bonding scheme. So you can see each bond is a different value of energy. Notice too that you've got single bonds, double bonds, and triple bonds. And since you have more pairs of electrons to separate, as you go from single, double to triple, the amount of energy increases. So what we're going to do is do chemical reactions that involve just what you see here, so that you don't have to go looking up bond energies anywhere else. You have them in your appendices. So that's what we're going to use to solve bond energy calculations, and that's where all the numbers are going to come from in the problems that we practice. So now as we move on, let's think about what needs to happen. Okay, in order to do a chemical reaction, two things have to occur. Number one, you have to break the old bonds. So you have to put energy in. So that's an endothermic process. Breaking bonds is endothermic. You have to put energy in to break bonds. And then you have to rearrange the atoms and form new bonds. And when those new bonds form, bonds are a stabilizing process, so energy is released as those atoms become more stable. So energy to break bonds is endothermic. Energy when bonds form is exothermic. That's the amount of energy that's released. And so really, the delta H, the enthalpy of the reaction, is the difference between how much went in and how much came out. So it's really just a subtraction. But you've got to figure out the total energy on each side. So we're going to start off pretty simple. 2 moles of hydrogen plus a mole of oxygen gives you 2 moles of water. So we've got to think, what kinds of bonds are going to have to be broken? Well, you've got 2 H bonds that have to be broken. And then you've got an oxygen bond, but remember, this is going to be the hardest part of doing this. You've got to remember what kind of bonds there are. So oxygen is actually held together with a diatomic bond. So we've got to break those, a double bond. You've got to break those bonds, and then we have to form new HO bonds. So here's the amount of energy that it's going to take to break all those bonds. We've got 2 HH bonds, and if you look at your sheet, an HH bond is 435. And then an OO double bond is 498. So that's where I got these two numbers. 2 times 435 is I'm going to have to add 870 kilojoules per mole to break all of this. Then I'm going to have to add just 1 mole worth of energy to break the oxygen double bond, so that's another 498. So the total amount of energy that has to go into the system to break the bonds, so this is a positive energy. This is how much energy you have to add to the system to break the bonds. Once we break those bonds, we need to reform new bonds from the product side. In this case, we've got 2 water molecules, but each water molecule has an HO bond. If you remember, water looks like that. And we've got 2 of these. So we've got 1, 2, 3, 4 HO bonds to form. So again, you look on the pink sheet, and an HO bond has the value of 464. So 4 of those times 464 means 1,856 kilojoules. Oops, you can't see that. 1,856 kilojoules is the amount of energy that's coming out of the reaction. So that's the negative part. That's how much energy gets released. So this is the endo part. This is the exo part. All right, so then what do? Well, I'm going to add these 2 numbers together. So this is how much goes in. This is how much comes out. If I add those together, I get a negative 488 kilojoules per mole. You can also think about it, you just need to take the difference of these 2, and what sign do you give it? Well, whichever number is bigger. So in this case, the negative side is bigger, so I know that I'm going to wind up with a negative value for the overall reaction. So overall, this reaction is exothermic. I'm going to do this reaction and release a total of 488 kilojoules per mole of reaction. So I can write that reaction like this, 488 kilojoules on the product side, because it's an exothermic process overall. More energy is coming out than what you had to put in order to change the bond structure. So it's a pretty easy process. The hardest thing is making sure you have the bonds right. So that's actually going to be your challenge. If you flip to the back side of the organizer, you will see that I'm starting to wean you off of information as you get from the top to the bottom examples. Okay, so let's just do this second one together. Or you can pause it, try it on your own, and then turn the video back on. That's absolutely okay. So I drew the structures for you because, again, you're a little rusty. It's been a few units since you've had to draw a structure. So I've drawn the structures for you. So there's a triple bonded carbon here. There's a double bonded carbon here. And then you have single carbon-hydrogen bonds and then an HH bond. So you've got to calculate the energy needed to break all those bonds first. So you've got to add up. So here's the entire reactant side. Everything on the left side of the arrow you have to consider. So you've got 2 CH bonds. You've got 1 carbon-carbon triple bond. And you've got 1 hydrogen-hydrogen triple bond. So you look at your numbers. You see that hydrogen is 435. You see that a carbon-carbon triple bond is down here, 837. And you see that a carbon-hydrogen bond is 418. Oops, 414. Sorry. And so you get 828, and you get 837, and you get 435. So if you add all those up, that should give you 2,100 kilojoules. So that's the amount going in. That's the positive stuff. That's the energy going in. The endothermic part. Okay, what are we coming out with? Well, we've got 1 molecule coming out. There's 1 carbon-carbon double bond, and there's 1, 2, 3, 4 carbon-hydrogen single bonds. So carbon-hydrogen, again, is 414. A carbon-carbon double bond is 611. So you've got, what is that, 1656 and 611 for a total of 2237. Okay, that's how much is coming out. So we've got a little bit more coming out than going in. So you should subtract those two to find that the delta H is going to be a negative 167. So 2110 going in, 2267 coming out. So overall you get a negative 167. And again, those units, kilojoules per mole of reaction. It's per mole of reaction. So this number applies to this whole thing. So I would take this number and put it, if I wanted to write a thermal equation, I'd put it up there, 167 kilojoules. So that's for the whole reaction. So that's 167 kilojoules per 1 mole of this, per 1 mole of that, or per 1 mole of that. But 167 for the whole reaction. If I had coefficients here like I did on the front side, let's go back and look. Okay, so this is, I'm going to write it up here so you can see it again, 488 exothermic. So that's 488 kilojoules per 2 moles of water, per 1 mole of oxygen, or per 2 moles of hydrogen gas. All right, so you've got two more, you've got two more problem sets, or problems to work on. Practice those. We'll answer questions tomorrow. Be careful. Here you've got oxygen and you've got CO2, so be careful about those structures. These are pretty straightforward. This one, be careful with this one. These are pretty straightforward. So be careful. The hardest part is getting the structures right. Once you get the structures right, it's easy to pick numbers off the table and multiply by a coefficient and so forth. But you got to make sure that you get the right kinds of bonds. Notice you've got your answers over here so you can double check yourself. But again, I've kind of weaned you away. Down here I give you only the overall answer. So we'll see how you do with that. Good luck.